Okay. In this video, we're going to just do a quick review of some of the most common types of volume questions that are found on the AP exam. And I'm not going to actually solve any of the integrals. I'm going to rely on the fact that if it were a calculator section, you could use f and int. If it was a no calculator section, you would find the antiderivatives, use fundamental theorem part 2, and actually evaluate it. The two functions in question here that we're going to use the entire time are the y equals the cube root of x and y equals x. Okay, these are our two functions we're going to use the entire time. Okay, so if I want to find the area, of course I just do the integral 0 to 1 of the function that's on top, which is the cube root of x, minus the function that's on the bottom, which is x, dx. That's it. Okay. Usually part A of a free response question would be just finding the area. Next, we're going to find the volume if it's rotated around the x-axis. Okay, I'm going to get rid of that so we have a little room to write. So, if I revolve this around the axis, what I end up with, revolving each piece is kind of a hollowed out bowl or something. Okay, have kind of a weird shape, and each cross section would look like a washer because it would have an outer circle with kind of a hollowed out inner circle. So if you think about this, I'm just going to write cross section right here. Okay, you look at it head on, you'd have a circle, and then you'd have a circle on the inside. And you get the big radius by evaluating the big function, cube root of x, and the little radius you'd get by evaluating the little function. And of course, when you're doing when you want to find the area of the donut or washer, you simply do the big circle minus the little circle. You notice I could factor a pi out. And this is the form that I usually use because we're going to integrate. Whenever you want volume, you integrate the area of the cross section. So I'm going to have pi up front. I like to have my multiplier up front. We're going to integrate from 0 to 1. We're going to have the big radius squared. The big radius was the bigger function, so cube root of x squared, minus the little radius, which was just x squared. And this is how we will get the volume. We simply integrate the area. Okay. You'll notice that each piece, each function had to be squared, and that's because each radius was squared. It was pi multiplied by the big radius squared, pi multiplied by the little radius squared, and then the difference. Okay. I'm going to get rid of this so I can continue drawing. And again, we want to make sure that we're squaring everything separate. We're going to use this form of pi multiplied by big R squared minus little r squared. Alright, next, if I was going to rotate around the line y equals -1. So now you're revolving like this. So what you did here is you made a bigger circle. Okay. Well, before, all it took to get the radius was evaluating the function, but now I made that radius 1 unit bigger. Okay, each radius I made 1 unit bigger than it used to be. The big radius used to just be cube root of x, but now it's the cube root of x plus 1. So if you're revolving around something below the axis, you're making the radius bigger. So we need to reflect that. We got pi. Still going from 0 to 1. I'm going to have the cube root of x plus 1 squared, because that's the new big radius. The other little radius will be x plus 1. And it's still integrated, because we integrate the cross-sectional area to get volume. So, if we were revolving around the line y equals -5, we would take the function and add 5 to it because we've made the radius 5 units bigger. It really just has to do with how we calculate the size of the radius. Okay? Next, we're going to revolve around the line y equals 2. Okay, so once again, let me just erase all this so I've got room to draw. Okay, so revolving around the line y equals 2. So now we're going up here. Like that. So now we're rotating up like that. Now remembering that a function tells us how far off the axis we are, I want to know how far the function is from 2. So if I say, well, the whole thing, the whole distance from the line to the axis is 2, I'd find the distance from the function to the line by subtracting 2, 2 minus the cube root of x and 2 minus x. Now you'll notice the big radius now is given by the linear function. So now when I integrate from 0 to 1, I'm going to do 2 minus x squared. That's my big radius. It's 2 minus the function. And my little radius is 2 minus the cube root of x squared. Like that. Okay? And again, it's because the function tells us this little darkened area, this part I bolded, but we don't want to know that. We want to know the distance between 2 and the function. So we can subtract off the function's value to figure out what the radius is. Okay? These are the most common types of revolutions, but let's also talk about them if we were revolving around the y-axis. So if we revolve the same thing around the y-axis, okay, now we're talking about it looking then something like this, when we revolve it around. We have to change our functions. So, before we said, well, y was equal to the cube root of x. Well, that means x is equal to y cubed. Okay, I'm just going to put a little star by that because we're going to use that. And of course the other was just y equals x, so now we'd say x is equal to y. Now this has to do with the thickness of your cross section, the fact that we need to do this in terms of y. You should have learned that in Calc 1. If you need a little review on that, I certainly can give that individually, but I'm going to try and keep this short. So revolving around the y-axis, we're going to need to do dy. Okay? You'll notice the big radius was given by the linear function. Well, that was just y, so y squared. Minus, the inside function was given by what used to be the root, but now would be the y cubed function, so y cubed squared dy. Now the bounds in this case, we used to always go from 0 to 1, and in this case the bounds are the same, but you got to remember to change just in case. You're going to go 0 to 1 because it's in terms of y. You no longer want to track along the x-axis, you want to track along the y-axis. So our bounds would be 0 to 1. They are the same, but that's only because the intersections are the same in both x and y. Okay? Now, if I want to revolve around the line x equals -1, okay, and that's over here, you got to think, well, what happened to the radius? It used to just be the function. Well, now I made it 1 unit bigger. So now, oh, and I forgot my pi in the previous one, if you were wondering, I apologize. Now, we're going to say, well, it's pi 0 to 1 still, and it's going to be y plus 1, we made the radius bigger, minus y cubed plus 1 squared like that. Okay. And if I were revolving around the line x equals 2, that would be over here somewhere. So now, kind of similar before, you say, well, 2 is the distance from the axis to the line, so I've got to subtract off the function. So it's going to be pi 0 to 1. We're going to have 2 minus the y cubed this time creates the big radius, minus 2 minus y squared, like that. Okay. These are kind of all the big revolutions. Okay, now, the area is the base of a solid with cross-sections perpendicular to the x-axis. Find the volume if the cross-sections are squares. Okay, so what's being said here is that we're dropping a line down from the, between the two functions that would be perpendicular to the x-axis, and then we're building up off of this little three-dimensional squares. These are my picture. It's hard to draw these, with any real accurate representation, but they're supposed to be kind of coming off the page at you. How I always think about it is, remember, we're trying to find the area and then integrate it. That gives us volume. Well, the area of a square, we've got base, and of course this is also, so the area would be base squared. Well, how would I get the base? Well, each base is simply the top function, it's the distance between the two functions. So the base is equal to the cube root of x minus x. So the base squared, the area, would be equal to the cube root of x minus x squared. So to find the volume, I simply integrate that area equation. Okay, cube root of x minus x squared. Notice now you're actually finding the difference between the functions and squaring it, as opposed to revolutions where you must evaluate the them separately and because they each represent a radius. Okay. Now let's do the next problem, which is semicircles. Okay, so let's say I was building semicircles. I'm going to leave that other work there on squares. We're building up semicircles. Well, a semicircle, the area is 1/2 pi multiplied by the radius squared, because it's just half of a circle. Well, thinking about the squares, the difference between the functions represents, not the radius, unfortunately, it represents the diameter. So the radius would be your difference between the functions. Oops. Be the cube root. Let's see if I can do that. Cube root of x minus x, but then we're going to have to divide that by 2, okay, to get the radius, because the difference between the functions is the diameter. So my area would be 1/2 pi multiplied by the cube root of x minus x over 2 squared. So again, I just integrate 0 to 1. I like to put my constant multipliers out front. And we've got the cube root of x minus x over 2 squared, like that. Okay. Finally, what if we were building rectangles whose height was 3 times the base? So now I'm still dropping that base down like this, still doing this, but now it's a tall rectangle. Okay, so let me just write this right over here. Area, of course, this would be b, this would be 3b, so the area would be 3b squared. Well, we already said what the base was, It's just the difference between the functions. So now my integral would be 3 multiplied by the base squared. So 3, the integral from 0 to 1 of the cube root of x minus x squared. And of course, the only thing that could change is what if we were doing cross sections perpendicular to the y-axis. So here they are, same exact problem, but this time with y-axis. So here, now we're building our squares like this. Okay, area is still the base squared, but now of course the base is x minus y, y minus y cubed. So to get the volume, we integrate that. And again, remember, the bounds here just happen to be the same. We are going in terms of y, so we have to think about, using the y-axis to set our bounds. So it's going to be y minus y cubed squared. Semicircles will still have that 1/2 pi out front. Integrate from 0 to 1. And remember the difference between our, I gotta put a dy, the difference between our functions represents the diameter, so we have to divide by 2 to get the radius. And here I change it to be the height is 4 times the base, so it would just be 4, the integral from 0 to 1, like that. This is really just all the different kinds of volumes. You need to be careful about, is it being revolved around the x-axis or the y-axis? Is it being revolved around a line below the axis or above the function? Are the cross sections perpendicular to the x-axis or y-axis? So just read the problems carefully and you'll be fine.